Alright, electrostatics. I'm not going to go through this in a lot of detail because I want you guys to go and watch the videos. It's all in the videos. But just something where they sometimes do penalize you guys is over here. If you have a positive charge on its own, you draw straight lines perpendicular to the surface. Take your time to draw these diagrams. Don't draw them in a rush. Take your time. Use a ruler. It goes out of positive because according to the definition of an electric field at a point, there's a difference between the definition of electric field and electric field at a point. Okay, they normally ask for this one. This is the important one. At a point, they say, is the electrostatic force per unit positive charge. In other words, in which direction will a positive charge move? If you put a positive charge in the presence of another positive charge, what's going to happen between them? They're going to push each other away. They're going to repel. So therefore, the field lines are out or away from a positive charge. If we look at a negative charge and we put a positive test charge in its field, that test charge is going to be attracted to the negative, and that is why the field lines go in. But please don't draw arrows like this. It's so confusing to mark. Draw your arrows like that, please. Okay. They normally don't ask for single diagrams. They put them together. Now, for some reason, they're being very strict over here. So if you have positive and negative, make sure that they bend towards each other. This one over here on the outside is straight. But these ones, take your time. These ones are curved like that. Okay. They have to be curved. They go out of positive into negative. Take your time, go and practice them. This question will be out of 3 marks. You don't want to miss 3 marks. It's easy 3 marks. In this case over here, notice that it bends all the way around. It bends all the way around. No lines cross each other. And over here we have the straight line. The lines are everywhere. That's 3 marks. Don't lose your 3 marks. Remember, when you add together the electrostatic force or the electric field, it is vector addition. So when it's vector addition, we take into consideration positive and negative direction. But when you plug into this equation or this equation or that equation, you only plug in the magnitude of the charges. Because to determine direction, you don't use the formula. To determine the direction of the force, you say, is it attractive or is it repulsive? To determine the direction of the field, you say, where will a positive test charge move? Okay, again, you go into the Junior Tikkie website, you go under grade 11, you're going to see all of the videos that I created for grade 11 electrostatics. It's exactly the same content, it doesn't change. So go and practice using those videos, please. Okay, I'm going to pause. I think you guys can take a break. Okay, so now we're looking at your favorite electric circuits. Okay, for your electric circuits, these are grade 10 formulae. Don't come up often, but it's always helpful to remember them. Ohm's law can be tested in an actual question, or they can actually test it in the way that they did in grade 11. Remember in grade 11, you guys learned of ohmic versus non-ohmic conductors. And when you have an ohmic conductor and you plot, for example, current versus potential difference, you know you're going to get a straight increasing line that passes through the origin. Because for an ohmic conductor at a constant temperature, as the potential difference increases, the current increases, we say they directly proportional. An ohmic conductor is a conductor that obeys Ohm's law. Okay, so don't forget that. They can ask it. It does happen. The other type of conductor you have is a non-ohmic conductor. And normally non-ohmic conductors will start off like this and then they do that. Alright, what basically happens is as time goes by, as you increase the current, the temperature in them builds up so much that they no longer follow Ohm's law. That's your non-ohmic conductor. If it does that, or if it goes like that, then you know it's a non-ohmic conductor. There are 2 types of non-ohmic conductor. You get a lot of metals that are non-ohmic, but then you also get your semiconductors. And I think your semiconductors are the ones that do that, while your non-ohmic conductors like tungsten wire in a light bulb, they do this. Okay, they can test that. Based on my diagrams, what is my independent variable? The current. You guys must never forget the stick and the stone. Eh? The stick falls onto the x-axis when the wind blows, and therefore in this case we know the current is the independent variable. For these Ohm's law experiments, they like to make use of this device. What is this thing called? A rheostat. Another name? Variable resistor. They like to make use of those, so don't forget about them. Okay. Then you have that formula for EMF, E equals V, I think that is external plus V internal, or we can say EMF equals V load plus V internal, or you can expand it like this, or you can write it down like this as well. It all refers to exactly the same thing, but on your formula sheet you're going to see this version, so always start off with what's on your formula sheet, and then go to the one that is useful for your purpose. Okay. These are just simple, very, very simple circuits. We have a series circuit and we have a parallel circuit. In this section in grade 12, we no longer just loosely use the term total resistance. Total resistance is going to be, in this circuit, the sum of these plus the internal resistor. Okay, total means everything, including internal resistance. If we just want these three resistors, we'll instead say calculate the load, or we'll say calculate the external resistance. Okay, so you guys must read very carefully. In this case, you know the formula. Please write down the formula first. In your trial exams, they gave a mark for writing this formula down. They don't always do it, but rather be safe so that if they do, you're going to get your mark. As mentioned, total resistance is both of them together. In a series circuit, you know the current is the same throughout. So we say R1, 2, and 3 are in series with the battery because the same current flows through the battery and through them. That's why they're in series. If we're looking at V external, in series, potential difference is divided. There is no voltmeter, right, that I know of that you can connect in a circuit that is going to measure V internal, the lost volts. Another name for V internal is the lost volts. This should have been lost actually, now I remember. Okay, there's nothing that can measure V lost. The potential difference that is lost is lost. We call it lost because we can't detect it. We can only detect that it's missing. Okay, so over here, this potential difference across the battery is called V external, and it's going to divide between the three resistors because potential difference divides in series. So the potential difference across this one plus that one gives you V external. Then the EMF, the total possible potential difference that this battery can deliver, is going to equal to the total current multiplied by the load plus the internal resistance. Coming to your parallel circuit, in this case we know that the current is going to divide, some goes there, some goes there, some goes there. But since these resistors are in parallel with the battery itself, we know that if we connect a voltmeter here, that voltmeter is still going to measure V external, but it's going to be the same across these three because in parallel, potential difference is constant. Okay, so start off with your formula. The total resistance will be Rp plus R. Some of you did, I'm going to call it silly things in your test. You tried, or your trial exam, you tried to combine this formula with that one. Never do that again, please. Calculate the one thing. When you're done with that, use the next formula. Plug it in, calculate the next thing. Don't try to be smart. You're not checking to see if you're smart, we're checking to see actually if you're wise. If you know you don't need to impress me, you just need to get your marks. Okay? So don't make weird formulas, don't put them together, calculate one thing and then the next. In this case, the current divides, so the current here plus there is equal to the total current. And we have the same formula, but here the load is Rp. Now, before we look at that graph on the right hand side, which is similar to what you got in your trial exam, I just have a random question here. If you go into the pack that I've given to you, this is somewhere towards the top of the pack. So MDE September 2019. Let's see. So this is not the pack that I gave to Junior Turkey. It's completely different if you were there. Page 51. So you're just going to have to like page about what's 50 divided by 4? Something like that. That number of pages. Okay, so somewhere around page 12 you should find it, maybe. Okay, but MDE September 2019, if you want to look at it. MDE September 2019. It's the physics pack. Have you found it? Has anyone found it? Really doubt that you guys will ever get circuit diagrams as simple as these ones. These ones are just here to remind you of the principles. You're more likely going to get something that looks like this. So being able to apply the logic at the top to this is important. Here is a battery. It has an internal resistance 1 ohm. Okay, as I said to you guys, whenever you have a circuit, before you do anything else, determine how the current is going to flow. So I'm going to close my circuit or close my switch, and then I'm going to say current, which is the flow of positive charges, is from positive to negative. So it's going to flow out this side. Let's get the color pen. It's going to flow out this side and get to this point. At this point over here, the current is going to split. Some's going to move down that path. Some's going to move down this path. Okay, let's use a different color here. This is going to flow all the way around like that. Be careful of voltmeters. They often cause confusion. Then the current is going to come together and it's going to join over there. So what do we have? We have a main part of the circuit. The main part is that is in series with the battery. The current that flows through the battery is the same as the current through the 80 ohm resistor. Do you guys see that? Okay. Now, over here, this is a parallel connection. This is the worst circuit you can get because inside of the parallel connection is a series connection. So you guys are going to have to follow with me. We can simplify this circuit to something like this. A light bulb, a parallel RP, and just like that. This is series. They're connected in series. So please understand that whatever is measured by V1 is not all going to go there. It's not all going to be measured across this connection. Potential difference is divided in parallel, so it's going to split. Okay. Once it is done splitting, we can now go and we can say, okay, but this is not one resistor. It's actually a few resistors. So let's get rid of the one and let's go and draw in the other one. So first we have this one, R1, like this. Okay, there's R1. Is it R1 or R2 or R3? It's R3. Okay, there's R3. We know that whatever is measured across the parallel connection is measured across the R3 because R3 is alone in its part of the parallel connection. Then on this side over here, we have two resistors, R1 and R2. Across both of these, we have the total potential difference or the potential difference across the 3 ohm resistor. Let me draw it better. This diagram is horrible. Or let's just go back to this. Starting off, the potential difference is going to divide. Some of this is going to go there. Some of it is going to be supplied to this part of the circuit. The complete potential difference across this one is measured across both of these. But what happens to potential difference in series? It divides. So this total potential difference here is going to be split between those two. Okay, don't assume that just because we have a parallel part of a circuit that all of this goes to the parallel connection. You need to say, okay, we have series in a resistor in series with the parallel connection, potential difference divides. We have within that a series connection, potential difference divides, and you have to take it from there. Okay, I'm going to let you guys do this in a moment. I'm just going to quickly finish this off, and then I'll let you guys do or work on that. If you guys have a graph, please remember, now this is a graph for grade 12, right? Where you have current and volts and there is internal resistance. If they say use the graph to determine values, the y-intercept is the EMF, the gradient is the negative of the internal resistance. You must take the negative to get the internal resistance. They can switch these values around to make your lives difficult, but I doubt they'll do so. So if they say using the graph, please use the graph. Here at the bottom, all of the formulae for work measured in joules. Another name for work is energy dissipated. We have formulae for power. Work has the symbol W. Power has or is measured in watts. Don't get confused. And then we have cost. I want to show you guys a question on cost. So here's a question. It was taken from a grade 11 paper. But if they really want to, they can ask you to calculate the cost of anything that is using up electricity. They say, you guys don't have this question, but they say there's a 220 volt washing machine that draws a current of 20 amperes for 2 minutes. The price of electricity is 1 rand 15 cents per kilowatt. When we are trying to calculate cost, we take the energy in kilowatt hours and we multiply it by the tariff, which will be in rands per kilowatt hour, like that. Here they gave you the potential difference, they gave you the current, they gave you the time. Step number 1, we need to find out what the power is of this washing machine. Power is equal to V times I. So we're going to say 220 times 20. I need you guys to please plug this into your calculators for me. I think it's 4400 watts. Just check. 4400. Okay. This is power given in watts. We would like kilowatts. How do you go from watts to kilowatts? Divide by 1000. So this is equal to 4,4 kilowatts. Now if you look at your energy formula, or even just a power formula, power is energy per unit time. We know that the power in kilowatts is 4,4. We would like to know the energy in kilowatt hours. We're going to divide by the time, but we are working with hours. So what we're going to do is we're going to take this 2 minutes and we're going to divide it by 60 to go from minutes to hours. If I'm not mistaken, it's something like 0,03. Okay, 0,03, is it 33333? So here we put in 0,303333. When you multiply up, you guys are going to have to tell me the answer. W is equal to 64466. Okay, I'm going to round off to 7 there. This is in kilowatt hours. Okay, so what did I do? I used this to calculate the power, which I converted to kilowatt hours. I went to a power formula or the work or energy formula, and I calculated the work in kilowatt hours. Now to calculate the cost, I can simply say the energy in kilowatt hours multiplied by the tariff is going to be 0,14667 multiplied by 1 rand 15 cents. And in the end, what is the price? So we're going to make it 17. It's 17 cents to work or let this washing machine run for 2 minutes. That is the price. They don't always ask you to calculate the cost, but it is required. So that is why I went over this. Remember, this lesson is recorded. So if you guys want to go back and watch it and copy it down, when you have the time, go and do so. But this is an example of cost. You do not get the formula for cost, but you're going to be given the tariff. You're going to see the tariff is rands per kilowatt hours. So this should remind you, kilowatts is power, multiplied by hours is the energy, and then we multiply by the rands to get the cost. Okay, are we all right? Okay, so on that note, this same question that I gave you, that we looked at, I want you guys to try it, and we're going to just see if you're on the right track. So try the whole question. Okay, so these two questions are actually there to test your understanding of grade 10 work. But they're testing it in a way that you guys are not very familiar with. So they said there are 3 resistors, a light bulb and a cell. There's an internal resistance of 1 ohm. They're connected as shown. The resistance of the 3 resistors is given like this. And there's the resistance of the bulb. So they didn't give us a lot of information. But we see that the cross resistor R1, we have a potential difference of 3 volts. And we see running through resistor 3, the 6R, we have a current of 0.1 amperes. And there's a chance that we may be able to make use of those things to calculate the answers here. They say write down the value of the potential difference across resistor 2. Here's resistor 2. So we assume we put a voltmeter there and the switch is closed. What happens to potential difference in series? It divides. Okay, remember in grade 10 I used to say to you guys, the battery is the mother and the mother is going to take the food and divide it between the children. Which child is going to get more food, the older child or the younger child? The older, because he or she is a lot bigger and needs more energy. So in this case, what has happened is there's some potential difference that is measured across this entire part of the circuit. And what is happening is it is dividing there and it's dividing there. This resistor has a resistance of R. This is 2R. So since this divides in a ratio, if the 1-year-old is getting 3 volts, then we can come to the conclusion that the 2-year-old is going to get 2 times 3 volts, giving us a total of 6 volts. Okay, it divides in a ratio. If you want to, you can even write it out as a ratio. We have R to 2R, that is 1 to 2. We know 1 is 3, 2 is X. We cross multiply and we find 6. It's just a ratio. That's all that it is. And what did I use? I used the fact that potential difference divides in series, because that is a series connection. Okay, very important information. It's going to help you to answer the more normal questions. If you find that questions like this confuse you, don't think that the whole question is over. You guys must calm down and move on. Question 9.1.2 says calculate the current through the 2 ohm resistor 2. So there's resistor 2. Okay, now the only place where we know current, I actually don't like these colors. The only place where we know current is through this resistor over there. We know the current is 0.1 amperes. This resistor is connected in parallel with these two. Now I have a question for you. How does the current through this resistor compare with the current through this resistor? Bigger than, equal than, the same? Okay, you guys say the same. It's the same because they are in series. So what we know is that when the current gets to this point, it's going to divide. Some's going to go there, some's going to go that way. But unlike the scenario where the mother divides the food so that the one child who is older gets more food based on their size, in this case we remember resistance is the opposition to the flow of current. Therefore, current is larger where the resistance is lower. Don't forget that. Current is larger where the resistance is lower. If we look at this part of the circuit, in total, the resistance, this is in series, so we can say R plus 2R. That is 3R. Over here we have 6R. Where are we going to have more current? Through the 6R resistor or through this 3R, the total of 3R? 3R, because where the current is lower, where the resistance is lower, the current is going to be higher. Okay, the chargers are lazy. They want to take the easiest path. It's not the correct term, but you guys get what I'm saying. So if the current here is 0.1 amperes, and this over here is half the resistance, then it means 2 times the current can go this way, because 3 is half of 6. So to get the answer to 9.1.2, we say 0.1 times 2, which gives us an answer of 0.2 amperes. Okay, I use grade 10 logic, but it does become confusing because of the variables. And that's going to get you 1 mark here, 1 mark there. Okay, so I'm going to give you guys a bit more time, and then I want you to try the rest of the problems. When you get to question 9.4, remember here they say explain. So when you explain, remember bullet points. Okay, so when you are done with question 9.1, you would go and fill in the information. Then they said calculate the resistance of R1. So R1 we can calculate by making use of Ohm's law, V divided by I. That's going to be 3 divided by 0.2, which gives us a final answer of 15 ohms. Now the 15 ohms, so for a question like this, you have 3 marks, formula, substitution, final answer. That is the value of R. So that means that R2 is a 30 ohm resistor, and R3 is going to be 15 times 6, 90, 180. 180. 90, okay. Mental math. Okay, alright, so 90 then. Okay, so we go and fill those in immediately. They don't have to tell us to. Then they say calculate the EMF of the battery. So in order to determine the EMF of the battery, let's see what we would have done. We know this equals IR plus small r. Okay, we know this, or we can find that. We know this, and I think we can find the current. Is that what you guys did? Okay, so step number 1, we calculate the total resistance. To find the total resistance, first we're going to add these two together. So we're going to say Rs is equal to R1 plus R2. That is 15 plus 30, giving us 45. You do this first, no fancy manipulations. This entire thing is in parallel to R3. So we say 1 over Rp is equal to 1 over R1 plus 1 over R2. We just copy paste that from the formula. You don't need to necessarily use the correct subscript, okay? Subscripts are just there to help. We say 1 over 45, this, plus 1 over 90. Thank you. When you plug this here into your calculators, what did you get? The fraction. 1 over 30. So Rp is equal to 30 over 1, and that is 30 ohms. Now that is not the total resistance, yes?
What about the light bulbs?
We're still going to add it. We're still going to add it. So look here. First we take this. So this is like brackets in BODMAS. First we add that together. When we're done with that, we add this together in parallel. When we're done with that, we add those together. Okay. So now we're going to say Rs again is equal to the 30 from the parallel plus that is 80. These are big resistances, giving you 110 ohms. Are we happy? Okay. Now what is the problem? The problem is that we are looking for the current. So we already know across the parallel connection, we have 3 plus 6, which gives us a total of 9 volts. Okay, I don't know if that is helpful at all. (9 volts across 30. It can help us. What method did you guys use? If you used a method to calculate the total current.
Well, I said 0.1 plus
Oh.
Yeah.
0,1 plus 0. Oh, yeah. You can also do this the way that I did. So using this 9 volt and the total resistance in parallel, you can also calculate the total current. But I think, yeah, that's a bit unnecessary. So to calculate the current, we're going to say I total is equal to 0,2 plus 0,1, giving us 0,3 amperes. We have the total current, total resistance, or rather the external resistance, and we know the internal resistance. So now we say the EMF is equal to IR plus R. That is 0,3 times, what did we get? 110 plus 1. That's very, very small. And you guys plug this into your calculators, and the answer is 33,3 volts. Okay. Shoo, that's a lot. Yes.
Let's say I didn't write the resistors in series, but I did substitute it and the resistors in parallel.
So you took this and you subbed it straight in there.
I didn't write it.
But you didn't write that out. Okay, look, according to this formula, no marks were awarded for that. So you're going to get 4 marks. But sometimes they might give a mark there. So just according to this memo, they gave a mark for this over there, for that substitution. They gave a mark for finding the 30. Then they gave a mark for the 30 plus 80, not the final answer. They gave a mark for this formula at the top, this substitution, and that final answer. So there's quite a few things they didn't necessarily award marks for, like how you calculated this, how you calculated that. They didn't give marks for that. Okay, are there any questions? Please don't mess up how you calculate the total external resistance. Take it in steps. Don't try to rush it. Don't try to be smart. Just take it in steps. Follow what you know. The last question, 9.2.3, said calculate the power dissipated by the light bulb. For this light bulb, we now know its resistance, and we know the current through it is 0,3 amperes. So the formula that's going to work nicely there is P equals I squared R. Okay, you can always go and solve first and then go about this the long way, but it's unnecessary. And the final answer is 7,2 watts. No unit, no marks. Do we agree? It's fine. Any questions? Mark allocations, 1 mark for your formula, 1 sub, 1 for the final answer. No unit, no marks. And then comes the last question. Question 9.3 says write down the reading on voltmeter 2. Voltmeter 2, where is voltmeter 2? Here. But we have the reading. Oh, now the switch is open, I see. Okay, thank you. So now the switch is open. If you take this part of the voltmeter, you see, oops, we have what we call this infinite resistance. I think that's what they call it, where because it's open, the resistance is so high you can't continue measuring. And then on this side over here, it does connect to the battery. But since it's not connected over the battery, we know that the reading is going to be what? 0. V2 is going to be 0 volts. Remember, even if the answer is 0, include your unit. Okay. Sometimes they don't award a mark if the unit is not there. Question 9.4, they were very kind with because they gave you hints. They said explain in terms of total resistance and current. They don't need to do that. So a learner makes the following statement. When the switch is opened, the lost volts will increase. Explain in terms of total resistance and current why this statement is not true. When they ask questions about current or even lost volts, generally we're looking at this formula. I don't know if it's the correct one for, well, our purpose here, but we'll see in a moment. So first we go and we say, when they open up the switch, what are we doing? We're removing these two resistors, and those resistors were connected in parallel. When you remove resistors that were resistors in parallel, so we take resistors in parallel and we remove them, what happens is that the total resistance increases. Okay, when you remove resistors in series, total resistance decreases, but in parallel, total resistance increases. So we know R total is higher. Resistance is the opposition to the flow of charge. So if the total resistance increases, what is going to happen to the total current? It's going to decrease. If there's more resistance, there's less current. Okay. Now they asked over here for us to explain what happened to the lost volts. The lost volts is this part over here. In this formula, for a given circuit, EMF and internal resistance is constant. They don't change. So if the total current increases and we multiply it by a constant number, what happens to this total part? Becomes larger. Okay, if this number is 5, and first we said 5 times 2, we get 10. Now we're saying this is no longer 2, this is now 100. 100 times, what did we say, 5 is going to give us 500. Okay, so this increases, that is constant. Since this increases and this whole thing is V lost, we can therefore say that the total lost volts, what is happening here? Because it does increase. It does increase. It is true. Am I wrong? Did I miss something? Oh, the current decreases. Sorry, I wrote the wrong thing here. No wonder you guys are looking at me funny. The current didn't increase, the current decreased. Okay, yeah, you guys are, I can see in your faces, you're all looking at me weirdly. The current decreased. So since the current decreased, a smaller number times something is in total a smaller number. Are we on the same page now? Okay, and therefore the correct answer is that it decreases. So how are we going to explain this? Number one, we're going to say in words, the total resistance is going to decrease. You guys write it out as a statement. Since the total resistance decreases, the total current is going to increase. Since small r is constant, we therefore have that I multiplied by R results in a larger V lost. Okay, when you guys are done writing, I will state it again. Okay, so we say the total resistance decreases. Since the total resistance decreases, the current increases. We've mentioned our control, it's the resistance, the internal resistance, which is constant, and since I times R is the lost volts is going to increase. This here is the independent variable. That's what we changed.
How will it increase? Shouldn't it decrease?
Hey guys, it's time to go home. Let's back up and go. It's going to decrease. My apologies. Okay. So this over here, the total resistance, that is the independent variable. That's what we changed. As a result of us changing that, the current is going to decrease. This here is increase. Can we try that again? We said that when we remove a resistor in parallel, the total resistance increases. The current therefore decreases, and as a result, V lost decreases. My bad. I'm very, very sorry. So this resistance is the independent variable. As a result of it, the current, the dependent variable, changes. And since this is a constant, this is going to decrease. Is that okay, guys? Okay, did I cause major damage, major confusion? We're all okay? Okay. Okay, we're going to look at electrodynamics. There's not a lot I need to discuss here. I just want to remind you guys of a few things. Okay, there were a few mistakes in your trial exams. Remember, a generator is going to convert energy from mechanical to electrical. We turn it and electrical energy is generated. A motor takes electrical energy and changes it to mechanical energy. Think of a fan. It has a motor. We give it the electricity and it provides the rotation. That's the motor. Okay. You must learn your elements, but when we were marking the trial exams, they emphasized that for your DC generator, also known as a dynamo, by the way, you must refer to the commutator. So don't just say the split rings, refer to the split ring commutator. You can even just call it the commutator, but you must include the term commutator. Okay, so in your AC generator slip rings, in the DC generator split ring commutator. Your motor, the biggest difference is that you have a power supply. Remember, current always flows from positive to negative. Current is conventional current, from positive to negative all the time. The long side is positive because positive needs two lines. Here's one line, there's the other line. Negative only needs one line, so the short end is the negative side, okay? I showed you guys this with your fingers as well. So moving away from this, the graphs are very important. For AC, this is one full rotation. For DC, this is one full rotation. Often you guys see two bumps and you think it's two rotations, but that's not true. This is one complete cycle, okay? I taught you guys when it comes to your motors, remember the alphabet, L, M, N, O, P. The left hand is for the motors. We always have, for both sides, it's going to be your force, your magnetic field, and your current. Okay, just remember that. Force, magnetic field, current, all the time. Okay? This equation, I taught you guys last year. You didn't perform calculations with it, but I did show it to you guys. And this year can come up in the multiple choice or even just in the longer questions where they ask you to explain something. So they can say to you, we have, now Faraday's law is for generators. Okay, we are changing the magnetic field to induce a current. So over here you're going to see based on the principle of electromagnetic induction. They can say to you, we have, let's use an AC generator. And they say for this AC generator, how can we increase the EMF? Okay, EMF is just potential difference. That is what it is. If you have an EMF and the circuit is closed, you're going to have current. So how can you increase the EMF or how can you increase the current? You look at this formula, it's on your formula sheet. There are two ways, actually three ways. The first method is we can use stronger magnets. If you use stronger magnets, this is what's going to happen to the graph. The graph is going to go from this to having a larger amplitude. But notice the period, the frequency has not changed. I did not squish the graph. I did not make the graph longer. It stays exactly the same. Okay. If we're looking at the one on the right hand side for your DC, if we use stronger magnets, it's going to do this. Alright, now that's the first thing we can do. The second thing we can do is we can turn the armature faster. So we can make those rotations happen more quickly. In other words, so we make faster rotations. And if it's faster rotations, we're taking the time at the bottom and we're decreasing it. That's the second thing. Now the thing about changing the rotations is that it changes the frequency. So if you're going to rotate faster, two things are going to happen to the graph. Let's say that you are rotating at twice the speed, so you're doing it 2 times faster. What is going to happen is this graph is now going to still be high like that, but it's going to be squished like this, you see. So in the same time, in the same amount of time, we've completed 2 cycles. Do you guys see that? over here, in the same amount of time, we will have completed 2 cycles. That's what's going to happen if you change the time. So faster means time is smaller. More speed means time is shorter. Please remember that. Your magnets change just the EMF, but more or faster rotations changes the frequency as well. They can ask you to draw this. They can ask you to identify it. They can ask you to explain it. Whenever you're asked to do so, go to Faraday's law. Normally our armature is just 1 coil, so just 1 turn. But you can actually go and increase the number of coils, and that will also increase the EMF without changing the frequency. Yes? The EMF is going to increase. Look here. Here is my formula for EMF. So if the time decreases, the EMF is going to increase. You see, so in both cases, stronger magnets and fast rotations, the EMF is going to be higher. The trick is when you do faster rotations, then the frequency is fast, and that's why the graph is squished. Okay, so as soon as you guys see squished graph, or if you see the graph becomes like this, it means we're taking longer or we're doing it faster. We happy? Okay, and that is this section. Alternating current. We are almost done. I was very, very happy with how you guys performed in the section on alternating current. I really don't have much to say yet. Just keep it up. Okay, keep going. Just as you did, keep it up. I'm going to go to the very last section, the photoelectric effect. Now, there were many of you, and I understood the logic, that neglected this completely. Okay, if you think you're the only one, you're not the only one. There were many learners who decided, you know what, there's just too much, I can't cope. I'm going to learn everything, and I'll get to this at a later stage. But this now, these November exams, that is your later stage, okay? So you can't do that again. Now you must master it. And what that means is when you study now, you're going to start with this, okay? Because that means if you start now when you're calm, when you start to study again, you'll at least go through this 2 times, at least. But if you leave this for last, then the day before your exam, you're going to go through it, and that is it. And that's the last time you're ever going to look at, see, or think photoelectric effect. We don't want that to happen. So the photoelectric effect is basically just the process where electrons are ejected from a metal surface. In order for them to be ejected, we need a suitable frequency of incident light. Incident means light that shines onto something. Okay, the incident light is the light that shines onto it. So in terms of the suitable frequency, we call this suitable frequency of light the threshold frequency, or the minimum. That is the minimum frequency of the light. Remember, frequency is related to energy. When light has a high frequency, like blue light, it has a lot of energy. When light has a low frequency, like red light, it has less energy. If we go through the electromagnetic spectrum, you'll think UV light, you think X-rays, gamma rays. X-rays can penetrate through your flesh and will bounce off of your bones. They can penetrate because it has a high frequency. Gamma rays can be used to destroy cancer cells. The reason they do that is because they have this high penetrating ability. So if ever you've heard of radiation, remember chemotherapy is one thing, radiation is a different type. We make use of electromagnetic radiation to destroy these cancer cells. Okay, so frequency is related to energy. The higher the frequency, the more the energy. Onto your metal surface, you don't just have to shine light of color, not just visible light. You can shine UV light, you can shine gamma rays, whatever it may be. But we normally would not go so high as to deal with gamma rays. Gamma rays are quite dangerous. Okay, so your threshold frequency is the minimum frequency needed to emit electrons from a certain metal, right? That is threshold frequency. The work function is basically E equals HF. Instead of using the symbol E, we're going to use the symbol W. That is still energy. I saw a lot of you were uncertain. EW, is it energy? Is it not energy? What's it measured in? And you left out your units, and so you didn't get your marks. But it's still just energy is equal to HF0. This here is the work function. It's basically the minimum energy required to emit those electrons. When you shine light equal to the threshold frequency, light that has energy equal to the work function onto a metal, we say the electrons are emitted but without velocity, without kinetic energy. Now guys, I'm going to tell you now, it makes no sense to me. I have thought and tried to understand this. I don't understand how something can be emitted without having a velocity. So I unfortunately can't explain it. But if you have energy equal to the work function shining onto that metal, electrons are emitted, but they don't have kinetic energy. I guess the reality is that you're never actually going to shine light exactly equal to the work function onto a metal surface. So there actually always is kinetic energy. Okay? Then we have the effect of intensity frequency. This is very important. I'm going to come back to it in a moment because I do believe I made a mistake in one of the videos that I recorded. Okay? And then the significance of the photoelectric effect, they rarely ever mention it, but I saw this in the exam guidelines, and it's simply that it illustrates the particle nature of light. Light is a wave, light is a particle. The photoelectric effect proves that it is a particle as well. Okay, so on the right hand side, these formulae still important, don't forget them. This E is, here's your metal. We're going to shine light onto the metal. What is the energy of that light? This is the energy of that light. And how do we calculate it? We say H times the frequency, or if they give you the wavelength, then we plug the wavelength into the other equation. Okay, so the E on the left is the energy of the light that is shining onto the metal. We happy? This over here is the work function, which is equal to HF0. This will be provided to you, or you may be required to read it off a graph. Then we have EK max. That is the maximum kinetic energy of the ejected photons. So this here is specific to the photoelectrons. You can call them electrons or photoelectrons. We use the term photoelectrons because they are emitted because they absorb photons. Photons, packets of light, energy. So that is your formula. All of these things, energy of the incident light, work function, kinetic energy, they're all measured in joules. It's all the same thing. Okay, so don't forget, many of you left out your unit. They're all just measured in joules. Sometimes you're going to be given a graph. Whenever they say use the graph to determine anything, you use gradient, y-intercept, x-intercept if possible. So for this graph of kinetic energy versus frequency, where it cuts through the x-intercept, did I make a mistake here? I don't remember. Oh, okay, no, I didn't. I didn't write it down. So where it cuts through the x-axis, that is the threshold frequency. Before the threshold frequency, there's actually nothing on the graph. Okay, so that is the threshold frequency. When light of a frequency above the threshold frequency shines onto the metal, then and only then does the metal have kinetic energy, and that is why the graph increases. Important question, is kinetic energy directly proportional to the frequency of the incident light? I'll say it again. Is the kinetic energy of the photoelectrons directly proportional to the frequency of the incident light? Sergole says yes. Anyone say no? How do you know if it's directly proportional? What are two things you look for in a graph? Straight increasing line. Second one, starts at the origin. They are proportional, but not directly proportional. Do you guys hear me? They're proportional. As the frequency increases, the kinetic energy will increase, but they're not directly proportional because it's only going to happen once we are above the threshold frequency. Okay, So once you're done plotting this graph, what you can do is you can extrapolate the graph. That means to pull it backwards so that it cuts through the y-axis. And here on the y-axis where you find the y-intercept, that is the work function. That is the minimum energy that must be incident on the metal for electrons to be ejected. So if they ask you to find the threshold frequency, it's the x-intercept. If they ask you for the work function, it's the y-intercept. The gradient here is just Planck's constant, and they rarely ask you for that. Okay. Lastly, we're almost there. Over here, you're going to see your absorption spectrum and emission spectrum. I tried my best to explain this in class, and I think after the second or third explanation, you guys were okay. Okay? But just be familiar with these things. The longer the line, the bigger the amount of energy absorbed or emitted. So in a lot of multiple choice questions, they'll do this. They'll say, here is, let's call it number 1. Then they'll go and they'll draw another arrow like this, number 2, and they draw another arrow like this, number 3. And they'll say, for which one, or for which electron, 1, 2, or 3, was the greatest amount of energy absorbed? More energy is going to be absorbed if we go all the way from the ground state to that energy level. Okay, this is not a good example. Let's say this arrow went all the way here. More energy is going to be absorbed there than in case 3 or 2. To jump, think of you jumping through floors, you're going to need more energy to go from the ground to level 2, 3, etc. So that's how you guys analyze it. And remember, if it goes down, then it means our excited electron is now wanting to be stable again. So in its orbitals, here's your nucleus. The electron is currently somewhere over there, and it's very excited. It has a lot of energy. So it doesn't want to hang on to that energy. What's going to happen is it's going to go back down to its ground state. When it does so, where does the energy go? The energy is going to be emitted in the form of light. Okay, so the bigger the jump, if we go from energy level 3 to the ground state versus energy level 1 to the ground state, the bigger the jump, the more the energy of the light. So from here to there, we may be talking, for example, blue light, because blue light higher energy. From here to there, we may be talking red light, because red light lower energy. Different atoms, different molecules will emit different colors of light. So if you're looking especially at your noble gases, look at helium, neon, argon, krypton, you can see they all have different colors. That is because the gases are emitting those colors of light. They absorb it, and then they emit specific frequencies of light. Okay, and that brings us to the end of physics. So what you guys must not do is, you must not go and just relax. Okay, you're going to relax when you get the marks that you want. I know you are tired, rest, but don't go and relax. You'll lose what we call momentum. Okay, momentum is a real thing, and if you rest for too long, you're going to lose the momentum. So as soon as you get the energy, or not even as soon as you get the energy, as soon as you get a little bit of the energy, you bounce back into it and you study. Okay, so it is now 11:30. The session officially ends at 12:30, but we can end it at 12. If some of you want to go on longer, we can do that as well. But I'm going to ask you guys to just try a few more problems before you leave. I know you guys are tired. Okay, I understand. Okay, so I'm going to pause here. So remember I said we'd get back to this, but it's very important. So number 1, they're going to ask you questions like this. They're going to say, what can we do to increase the current in the circuit? Okay, what can we do? Do we increase the frequency of the light, or do we increase the intensity? Or can we do both? What should we do? Okay, the intensity is brightness, and therefore the number of photons that is shining. The word intensity, the effect of intensity, intensity is the brightness of the light. Okay, another term for intensity is the brightness. Yeah, something like that. Okay, so if we would like to increase the current, should we increase the intensity or should we increase the frequency? or both? Okay, very important, guys. This is very important. I think it comes up in every single November exam. Current is equal to the number of charges per unit time. If we have a metal with a whole lot of electrons, what's happening is we are shining packets of energy onto this. When we go and we take the same light, assuming that the energy of the light is above the threshold frequency, when we increase the brightness, what happens is we start to put more packets. More packets are going to hit the electrons. If more packets are hitting the surface, more electrons can absorb energy. And what's going to happen? We're going to have more charges moving through the circuit. So grade 12 is very important. If you would like to increase current, you're going to increase intensity. It says here in your notes, the number of electrons emitted per time is proportional to the intensity. Provided the frequency is bigger than or equal to the threshold frequency, if you want to increase current, you increase intensity. Now, if you would like to increase the kinetic energy of the light, not the current, but the kinetic energy of the photoelectrons. In other words, let them be emitted faster. To increase the intensity, to increase the kinetic energy of the photoelectrons, you will increase the frequency. We say that the maximum kinetic energy of the photoelectrons is linearly proportional. You see here they use the term linearly proportional and not directly proportional. Because it's not directly proportional, it is linearly proportional. You guys see that? I did that to get you back because I saw you zoned out a bit. Okay. Frequency does not influence current. Hear me? Frequency does not influence current. You need the frequency to be high enough. But increasing it further will not make the current higher. To make the current higher, we increase the intensity. To make the kinetic energy at which they're only emitted, not how they move through the circuit, just emitted in your photocell. There we're going to increase the frequency. Are we happy? Don't forget this. Okay, so I think we're going to end here. There's a lot more I would have loved to do with you guys, but you guys do need to go and eat now. So thank you very much. I wish you guys all the best for your final exams. Study hard.